Let's take a look. Now that you've done the notes, let's take a look at some of these sample problems. All right. So number one, is there a relationship between Facebook use and age among college students? In a Unit 1 context, without doing a chi-square test, uh, we can still think about this. The following two-way table displays data for the 219 students who responded to a survey. Realistically, this is more of a Unit 2 question. It snuck in here. All right. We can still do it. Okay. What percent of students who responded were Facebook users? So just overall Facebook users. Yes. So we should add those up. So Facebook user, 78 plus 49 plus 21. And I'm just going to put that over here. I'm going to sort of add some totals just because I think that'll be useful. And then 4 plus 21 plus 46 is 71. And we know that there were 219 students total. So what percent of the students who responded were Facebook users? So responded yes to Facebook use over the total number of students. I did find my calculator in my jacket pocket. And that's going to be 0.6758. So percent would be 67.58%. Is this percent part of a marginal distribution or conditional? So this one is going to be marginal. Big picture, because we're getting it from the margins, right? It's just overall, Facebook or not. We haven't conditioned on some subset of the population. There's no given. Okay. What percent of the younger students in the sample were Facebook users? So now they just want us looking at younger students. So now we are conditioned on being younger. So there's 82 younger students overall. 78 out of the 82, this must be older data, were Facebook users. So that's going to be 78 divided by 82. 9512, so 95.12%. Versus what percent of the Facebook users in the sample? So now we're going to say of the Facebook users were younger students. So here's Facebook users is going to be this row. So now we're conditioning on using Facebook. So that's our denominator. And then younger students is still that same 78. So on top is both younger and Facebook. The denominator changes based on how we're conditioning it. Right here, it's of the younger students. So that's our denominator. Here it's of the Facebook users. So that dictates our denominator. So 78 divided by 148 is 0.527, so 52.7%. Both of those would be conditional probabilities. Okay, cool. Good question came up. When you get a table, don't worry about the conditional probability formula. Look at the table. The formula is really great when you just get the actual probabilities. When you have the table, I think it's much easier to just see it. All right. Great. Number 2, the first 4 students to arrive for a first period statistics class were asked how much sleep to the nearest hour they got last night. Their responses were 7, 7, and 9 and 9. Find the mean and standard deviation of this data set. Okay. This is a sample. It's not a great sample because it's the first 4 students, but that's okay. We're going to say 7 plus 9 plus 9. And that is going to be divided by 4 because there's 4 students. So we have 32 divided by 4, which is 8. The standard deviation, we're not going to do this by hand. That seems silly. You could, subtract this minus that and square it and do that with each one and then divide it up. No, thank you. So I'm going to instead put it in my lists. And I'm just going to do 7, 7, 9, 9. This is a really small data set. I should use this. List 1 is just going to be 7, 7, 9, 9. And then I do the calculate one variable statistics using list 1. No frequency list because I didn't use a frequency list here. I could have done this to get my mean as well. My standard deviation, and since it's a sample, I'm going to use the S. My standard deviation is 1.155. Interpret the standard deviation you obtained in part A. Okay, that's an interesting question to interpret the standard deviation. So, roughly, the standard deviation is, it's not quite the average distance from the average, but it's a measure of spread. So I'm going to say the standard deviation, so we're going to be specific, the standard deviation of the hours of sleep is about 1.155. Meaning a randomly selected student will vary from the mean by about that. Sure, let's say that. Randomly selected student will vary from the mean by about 1.155 hours. I don't know what that letter is, but it's not a letter we use. Okay. Do you think it's safe to conclude that the mean amount of sleep for all 30 students in this class is close to 8 hours? Why or why not? Okay. Do you think it's safe to conclude? So, like I already said, we have some questions about this sampling method, specifically the fact that it was the first 4 students to arrive. So, I would say probably not. The first 4 students to arrive is not necessarily a representative sample of all students in the class, right? Maybe the people who arrive a lot later got more sleep and they slept in, and that's why they're arriving later. Maybe they got less sleep because they're like cramming for the project due. Who knows, right? First 4 of anything, like this seems like a convenient sample. Hey, you're here. How much sleep did you get? Not a great way to conduct a survey. Okay, good. 3. Is the IQR a resistant measure of spread? Create a data set with 7 data points and use it to support your answer. So there could be a lot of data sets we come up with this. The first question is it a resistant measure of spread? And when we're talking about resistance, we're talking specifically to outliers, especially extreme outliers. Okay. I'm not going to answer that question first. I'm going to create the data set first, and let's let the numbers tell us. So a data set with 7 data points. 1, 2, 3, 4, 5, 6, 7. Okay. So let's, I don't know, 3, 3, 9, 10, 11, 13, and then let's put in one of really high outliers. One really high outlier. Let's say 50. I could use a random number generator for this, but I wanted it to be in order too because quartiles, all that. So, IQR. Remember, IQR is equal to Q3 minus Q1. So when you think about a box plot, this is Q1, this is Q3. So it's giving us basically the range of the box. So the IQR, since this is 7 data points, this is right in the middle. And Q1 is going to be the median of the lower half. So this is going to be Q1. Q3 is going to be the median of the upper half. So this is Q3. And so 13 minus 3, our IQR is 10. If this were 100, our IQR would still be 10. And so I would say yes. IQR is reasonably resistant. Now, the bigger the data set, the sort of more stable all our values are going to get, because one value is going to have less of an effect, especially if it's resistant. If I went much smaller than 7 data points, we could change the IQR just by dint of not having a ton of data. But yeah, IQR is a reasonably resistant measure of spread. Okay. Standard deviation. Okay, I'm playing around with this. Using the numbers 0 to 10 with repeats allowed, choose 4 numbers that have the smallest possible standard deviation. Okay, smallest possible standard deviation. I'm gonna translate this to smallest spread. And you could use any number here, because what's the smallest spread if not 0, right? If they're all the same thing. So I'm just going to I'm going to be crazy. I'm going to say they're all 10. 10, 10, 10, and 10. I wonder what proportion of you chose like 4, 5, or 6. Okay. So the standard deviation here is going to be 0 because every data point is 0 from the average. So now, using the numbers 0 to 10 with repeats allowed, choose 4 numbers that have the largest possible standard deviation. So we want the biggest spread. Here, there really is only one possible answer. 2 of them need to be 0, the lowest possible, and 2 of them need to be 10, the highest possible. The reason for that is the average is still going to be right in the middle. The average is going to be, what, 5? But these are as far away from 5 as you can get while still being within this boundary. Okay. So, is there more than one possible answer in part A? Yes. Any digit just has to be all the same. For part B, no. Have to maximize that spread. Okay. Onward. According to the National Center for Health Statistics, the distribution of heights for 15-year-old males has a mean of 170 centimeters and a standard deviation of 7.5 centimeters. Paul is 15 years old and 179 centimeters tall. Part A, find the z-score corresponding to Paul's height. Okay, so the z-score is actual minus mean over standard deviation. I would say always write down your formulas and then fill them in. So Paul is a 15-year-old male. His actual height is 179. His expected height is 170 centimeters. And the standard deviation is 7.5. I noticed a couple mistakes with this. If you're going to put it in your calculator and not create a fraction, make sure these go in parentheses before you hit enter. Otherwise, order of operations is going to do this first, the 170 divided by 7.5, and then it's going to subtract that from 179. That's no good. All right, so we have 179 minus 170 is 9. Divided by 7.5, we get a z-score of 1.2. And this is a really good time to pause and say, does that make sense? If I did my order of operations wrong, 179 minus 170 divided by 7.5, I get 156. That doesn't make sense, especially when we consider the fact that he's a little over, right? We can see he's 9 centimeters taller. He should be a little over 1 standard deviation away. But he shouldn't be 156 standard deviations away. That's crazy. So your z-score, if you get a number in the hundreds, like check your order of operations. So what this means is Paul is 1.2 standard deviations taller, right? Because it's a positive 1.2 than average. At what percentile does Paul's height put him? Okay, we could use the z-score here or the values. Let's do both. So if we wanted to use his z-score, we would say the lower is negative infinity. The upper is Paul's z-score. And then since we're using a z-score here, our mean is 0. And our standard deviation is 1. And so just for reference, here's 0, here's like 1.2. So we're expecting a percentile that's pretty high, right? Like he's definitely over the 50th percentile, probably over the 80th. When we did put this into our normal CDF, in our normal way, found my calculator, we get that he's at about the 88th percentile. If you were going to do this with the actual values, same process, 170 is our mean. 179 is up here. Notice I'm not marking every single standard deviation. I don't always need to do that, only when I'm using the empirical rule. This I'm just marking the mean and my point of interest. This time, say normal CDF, still going to negative infinity because it's that point and below. We could say 0 in this case because like no one's going to be less than 0 centimeters tall, but it's going to have a negligible effect here. His actual height is 179, the mean is 170, and the standard deviation was 7.5. When we put that into normal CDF, 179, we get the same 88th percentile. Okay. And for good measure, lower, upper, mean, and standard deviation. Okay. Either one of these is a totally acceptable method. Whatever makes the most sense to you is great. You do not have to do it both ways. Pick one or the other. Onward. Explain in at least one complete sentence what the percentile you found in part B means to someone who doesn't know anything about statistics. So, let's see if my typey will work here because we love my handwriting. I know you'll miss it, but okay. So I'm going to say Paul is taller than about 88% of all year-old boys. And I think this is in the United States. Yeah, it doesn't say that the National Center for Health Statistics is the U.S. National Center. We can sort of assume. Uh, Although on a real thing, we should be as specific as possible in our questions and our answers. Okay, so that's what the percentile means. He's doing better than or is taller than that percent. Okay. 6. Researchers in Norway analyzed data on the birth weights of 400,000 newborns over a 6-year period. Wow, it's a lot of babies. The distribution of birth weights is normal, with a mean of 3,668 grams and a standard deviation of 511 grams. Babies that weigh less than 2,500 grams at birth are classified as low birth weight. Now, before we dive into this, I want to point something out. The distribution here is listed as normal. It was not listed as normal here. However, it's reasonable to think that the distribution of heights would also be normal because 15-year-old boys' heights are probably clustered around some number. And then sort of fewer and fewer heights as you get further from that middle are represented. So it would be better if this said it was normally distributed. I may even verify and add that in for next year. But this is a situation in which it's reasonable to assume normality. Here, we're told it. So, what percent of babies will be identified as low birth weight? So again, we have, here's our mean, here's our standard deviation, and we want to say that weigh less than 2,500 grams. So I'm going to draw a little sketch first. My mean is 3,668. We want to know 2,500 and below. Seems like a problem for normal CDF. So we're going to say normal CDF, negative infinity at the low end, 2,500 grams at the high end. Here's our mean, and here's our standard deviation. Some of you, I've noticed, have taken to like writing the words out in the parentheses. That's fine. As long as it's clearly labeled, you're fine. So when we normal CDF this, we're going to get 2,500, 3,668, 511. And we get that about 0.0111 or about 1.1% of babies will be ID'd as low birth weight. Okay. Find the quartiles of the birth weight distribution. Okay. This throws people off. So we want to be careful. Quartiles, the first quartile, that's the same as the 25th percentile. And the third quartile, I'm going to put that over here. The third quartile is going to be the 75th percentile. This is something that you do want to know. The first quartile is the 25th percentile. The third quartile is the 75th percentile. So since we have the percentile and we want a value, we're going to use inverse norm in both cases. So here we're going to use inverse norm. Our area is going to be 0.25. The mean is 3,668 and the standard deviation is 511. Area, mean, and standard deviation. I'm going to do the same thing here, except now we want 75% to be below. But the mean and the standard deviation are going to remain the same. Okay, so now we'll run our numbers, inverse norm, 0.25, 3,668, 511, always with a left tail. Again, I'm not even writing it out as left because so many of you don't even have that option on your calculator. If you do, just leave it as left. So this is going to be 3323.34 grams is our 25th percentile, our first quartile. And then to get our third quartile, our 75th percentile, we run the same thing, but change that to 0.75. And that is 4,012.66 grams. Okay. Onward. This, pretty sure, is right off your first test. So, the average yearly snowfall in Chillyville is normally distributed with a mean of 55 inches. If the snowfall in Chillyville exceeds 60 inches in 15% of the years, what is the standard deviation? So, we don't know the standard deviation. We do have a percent. Now, exceed 60 inches. So this is where, when in doubt, draw it out. Thank you, Mr. Hill. Here's our distribution. We know the mean is 55. 60 is over here relative to 55. And we're talking about exceeds. So we're talking about this. So this right here is 15%. When we use inverse norm, we're going to plug in this bit. We're going to plug in that remaining 85%, right? Because 100 minus 15 is 85. So we're going to first get a z-score. Inverse norm. We have to get a z-score because we do not know the standard deviation. So we're going to say 0.85. Again, that was just 1 minus 15%. Because we want to know what's to the left of here. And then we'll say 0 and 1. When we do that, 0.85, 0, 1, not 511. We get a z-score of 1.0364. I'm only writing that out to so many decimal places. I'm going to leave that in my calculator with the whole decimal place running to use as a calculate. Now, to find the standard deviation, I set up my z-score formula. So z equals x minus mu over standard deviation. Now I know that my z-score is 1.0364 for 60 inches when we subtract a mean of 55 inches all over the standard deviation. Our algebra, we're going to get, I'll do the algebra out. So we're going to get 1.0364 equals 5 over standard deviation. We're going to multiply both sides by the standard deviation. And we're going to get 1.0364 equals 5. Oops. 0364 sigma equals 5, because those cancel out. And we're going to divide both sides by 1.0364. And we get sigma is equal to, and again, I left this with all its decimals in my calculator, so I'm doing 5 divided by, and then just grabbing that number. I get 4.824. So there's our standard deviation. All right, one more time. The mean and standard deviation of acidity pH of the water in Chillyville were calculated as 4.0 and 1.1 respectively using a miscalibrated meter. Okay. The pH meter was recalibrated and the lab techs reported that the measurements can be corrected by adding 0.1 pH units to all of the values in the sample and then multiplying the result by 1.2. What are the correct mean and standard deviations? So, without having all the values and doing that, we can use our transformations. Remember that for means, that's means, you do everything. For standard deviation, you only multiply or divide. Okay, so For the mean, we're going to do both of these things. So 4.6 plus 0.1, because it says this, and then multiplying the result by 1.2. So we're going to say 1.2. And when we do that, we get 1.2 times 4.7. And the new mean is 5.64. So that is the new mean. Chillyville has some problems. That's still a pretty acidic pH for water. Don't drink the water in Chillyville. All right. For the standard deviation, we're going to ignore the adding 0.1 because that adding 0.1, again, it's just shifting everything up by 0.1. It's not affecting the spread. What is affecting the spread is multiplying the results by 1.2. So we're going to say 1.2 times 1.10. And that's going to give us a new standard deviation of 1.32. Okay. Again, as usual, hope that was helpful. See you next time.